We're going to discuss oxidation states. Oxidation states' official definition is the number of electrons lost or gained by an atom. Now I've got my own special definition for this. It tells you the number of electrons either needed or required to give away for atomic stability. Well, what does that really mean? All right, so we've got some number of electrons. Pick one. So let's use hydrogen. Hydrogen on the periodic table is right here. Hydrogen. It has one proton and one electron. Okay, so we know it has one proton and one electron. Great. If we draw this in our first electron orbital, we have one electron. Now imagine a tire. That's a weird statement, isn't it? Of course. All right, this is my best attempt at drawing a tire, except it's going to be flat because there is more air on one side than there is on the other. That's not a very stable tire. We don't want that. What we're looking for is a tire that's equal on both sides, like this. This one's good, this one's not. That same type of wobble occurs here as well. This electron needs to have a pair on the opposite side. That's so that it's stable. The electron orbital that this is sitting in, this is called an orbital, will match a rule that is called the 2 in 2 rule. And what that does is it tells you the number of the electron orbital equals n will then feed into that 2 in 2 rule. So if it's in the first electron orbital, we're going to get the ability to hold 1 squared times 2 equals 2, because 1 squared is 1 times 2 is 2. The second n, so we'll just type this in or write it in. If it's n equals 2, then we're going to have 2 squared is 4 times 2 equals 8. We'll do it one more time. 3 squared is 9 times 2 equals 18. All right, hopefully you're following there. Because this can only have one electron, because there's only one proton there, it would be easier for this proton to eject the electron to seek stability with no electrons. That's what it wants. It wants that stability. So if it gets rid of it, it is going to have an oxidation state of +1. It has 1 to give away. Okay, so H equals +1. Everything on the periodic chart under hydrogen, that includes lithium and sodium, potassium, rubidium, and so on, those are all going to be +1s. Let's prove it. Here's lithium. Lithium has 3. Just in case I've gone too fast, you can rewind the video. Lithium has 3 electrons. It has 3 protons and 3 neutrons. I'll get to neutrons in a bit. It's got 3 electrons. Well, the first, here's our nucleus. The first 2 go in the first. Checked there. Then we have another electron orbital for the third electron, and there it is. It has 1 to give away. There's nothing to balance it out. So we call that a +1. Beryllium is +2. Well, beryllium is right next to lithium. I chose those because they're easy to draw. We could do this with any of them. So here's beryllium. It's a +2. So we go +1, +2. Let's prove it. Beryllium has 4 protons, 4 electrons, and 4 neutrons. Again, that's for beryllium, Be. So in the first electron orbital, there's 2. Here's 2 more. That equals 4 electrons. It's got 2. Although it is stable, it wants to get rid of those because of this right here. How many electrons does it want? 8. It only has 2. So it is easier to get rid of 2 than it is to absorb 6 or to gain 6 to add up to 8. Which means beryllium is a +2, and everything below beryllium is +2. That includes magnesium and calcium and strontium, so on. We can ignore these here in the middle. There's a reason. That reason is they've got multiple oxidation states, and we need to find out what those are by looking at the others that are reacted with it. Okay, so let's go over here. Let's go to fluorine. Fluorine has got 9 protons, 9 electrons, 9 neutrons. I'm going to change my sheet. Again, we're going to use fluorine. It has 9 protons, 9 electrons, and 9 neutrons. Again, we're focusing on the electrons because of the oxidation state. Here's fluorine. Here's the nucleus. We have the first electron orbital holding 1, 2, which means we've got 7 left. Okay, no problem. This is the first orbital. This is the second orbital. Going back, we have 2 orbitals. It can hold a maximum of 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 4, 6, 8, 9 all together. Does that make sense? Now watch. We've got that extra electron there. But would it be easier to get rid of that one and have these unbalanced, or would it want to attract an electron to pair up? In this case, it wants to attract it. It needs 1 electron. So fluorine has an oxidation state of -1. Everything under it will also have a -1. So let's look at our periodic chart. Fluorine, chlorine, bromine, iodine, astatine, those all have a -1 value. So if this is -1, what do you think this one is? -2. Let's prove it. Let's look at oxygen. Oxygen has 8. I'm going to put a dot in the middle just so it doesn't get confused. That's an O. Oxygen has 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. It still needs 1 there and 1 there. It is easier to gain 2 to balance those out so that it meets the rule of 8. It's easier to gain 2 than it is to get rid of 6. So oxygen, as I had predicted, is now -2, and everything underneath that is -2. So when we're looking at our periodic table here, I'm actually going to draw on this sheet. Give me just a second to find a marker. This is going to be +1, +2. We can skip those here in the middle, again, because they have multiple oxidation states. Boron, if you do it just like I showed you, will be +3. Carbon +4. Nitrogen +5. Oxygen +6. Fluorine +7. And then over here, way on the other side, the far right-hand side, those are called the noble gases, and they have a full octet rule. They have a total of 8 in each one of those, except for helium, because it only has 2. So 2, the second orbital can hold 8. That would be a total of 10, then 18, and you'll see it increase from there. With that, it really won't have an oxidation state because it's not going to react. Going in the opposite direction, now I told you that this was a +7 or -1. Fluorine, -1, that's where I got my number. We also proved that oxygen is a -2. -2, we can carry that forward, -3, -4, -5, -6, and -7. Now, just a rule of thumb, it's going to pick the smaller of the numbers regardless of the sign. Regardless of the sign. So in this case, it's going to pick -1. In this case, it's going to choose +3. That's for everything in this column. It's for everything in this column. If you don't believe it, go ahead, write out the number of electrons that you've got. You can find that number of electrons by looking at the atomic number. So to find out what our octet rule will be, we're going to choose one of those oxidation states and then work our way up when we look at chemical reactions. Any molecule can also be done this way. Watch what happens. Remember that octet rule, the rule of 8. If I want to react sodium, which we saw a while ago on the very far left-hand side, with chlorine to make table salt, that's known as sodium chloride, watch what happens. And I'm going to show you the periodic chart so we can get the numbers. That way it's not a surprise. Sodium is 11. Chloride is 17. So let's write down 11 and 17. Now those are pretty big. We're going to see a whole lot of electrons being thrown out there. Remember, sodium is 11, and we're going to find that sodium under hydrogen. Remember that +1. Chlorine, remember that it's going to choose the smallest. It's going to be -1. Watch what happens. Sodium. 2 in the first, 8 in the second. 1, 2, 3, 4, 5, 6, 7, 8. That adds up to 10 so far. One more, 11. Try it again. 2, 4, 6, 8, 10, 11. 11 in that third shell. It doesn't need it. It's going to try to get rid of it. That makes it a +1, just like we predicted. This is important. It's going to come back into play. Hang in there. We know that chlorine is 17. So chloride, we're going to do 2, 3, 4, 5, 6, 7, 8, 9, 10 altogether. And if we know there's 10 so far, there's 7 on the outside. 1, 2, 3, 4, 5, 6, 7. It needs 1. If it needs 1, it can borrow from the sodium and they will bond together. If we bond that, you'll get sodium on one side. I'm only going to draw this outside rim, this outside, we call it the valence shell, and I'm only going to draw this valence shell. So here's sodium with its valence shell. It has 1. Here's chloride with its valence shell, and it has 1, 2, 3, 4, 5, 6, 7. To balance that out, sodium is going to try to get rid of its electron by donating it over here to chloride. So chloride will now have 8. It will meet the rule of 8. And sodium will also meet the rule of 8 by getting rid of the one that it doesn't need. 2, 4, 6, 8. So it's perfectly balanced. You can get all of this information right here. This is the cool part. Watch what happens. Remember that it had 1 electron for hydrogen? It had 2 valence shells for lithium. Let me pull up my sheet here so you can see it. Hydrogen had 1 electron, or 1 electron orbital valence shell. Beryllium has 2. Lithium has 2. Sodium and chloride, 1, 2, 3. Watch. This is really awesome. At least it is in my book. It's at the top. It's in the first row. Hydrogen and helium. There we go. Hydrogen and helium. They only have 1 electron orbital. Lithium or beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, they have 2 orbitals. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chloride, and argon, they have 3 orbitals. Try it out. Then we have 4 orbitals here. This is important here later on. A lot of the chemistry that we're going to talk about a little bit later on. This part right here is relatively special. we have the s, p, d, and f orbitals. So our orbitals are going to increase in size. There's a reason, because of that 2n2 rule. So we're going to need even more space to hold those electrons, and we're going to hold on to that all the way to here. Then we're going to add even more, and you notice that number increases dramatically. Again, that's the 2n2 rule.